Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list published on September 8, 2025, about 3 days ago. The standout claim is that a new critic called floq uses flow matching and iterative computation to improve value learning, delivering roughly 1.8 times better performance on hard offline reinforcement learning tasks. The paper is titled, floq, Training Critics via Flow Matching for Scaling Compute in Value-Based RL. And as we'll see later, the implications for model training are quite significant. In short, the method turns a Q function into a velocity field that can be stepped multiple times, giving controllable capacity and stronger online fine-tuning. On X, posts highlight that flow matching critics outperform standard value learners, with gains driven by multiple flow steps that improve representation and error correction. One recap lists it as a top research item. Engagement appears moderate, with roughly 20 likes and a handful of replies across the posts. Alright, the previous segment highlighted the 1.8 times gain. Figure 1 presents the pipeline. A random scalar z at time 0 flows through k integration steps, guided by a learned velocity field, so the final z matches the q value. The inputs include the state, the action, a Fourier time embedding, and a categorical encoding of the current scalar, which stabilizes training. This setup lets capacity scale by simply increasing the number of integration steps. Alright, Figure 2 explains why certain design choices prevent flow collapse. The left panels show that a narrow noise interval produces straight traversals, so the velocity ignores the interpolant and behaves like a monolithic critic, while a wider interval induces curved paths that force conditioning on z and time. The right panels depict two stabilizers, a histogram like Gauss encoding that discretizes the scalar input, and a Fourier time embedding that makes step index matter. Okay, the previous figure focused on design choices that shape the flow. Table 1 reports offline results across 50 tasks, comparing behavior cloning, BRAC, SORL, FQL at 1 million and 2 million steps, and floq with default and best settings. The averages show floq leading on all environments, and especially on the hard subset, which matters because FQL underachieves there. The best floq configuration reaches about 1.8 times the FQL score on hard environments. Trigger text. Table 1 reports offline results. Bounding box 0.03, 0.20, 0.97, 0.93. Well, Table 1 showed broad offline gains. Figure 4 presents head-to-head statistics against FQL, covering median, interquartile mean, and optimality gap, and it places success rate on the x-axis. The colored bars for both default and best floq sit clearly to the right of FQL, which indicates higher success rates. Confidence intervals do not overlap, so the advantage appears statistically significant across all four metrics. Alright, the previous figure showed clear offline advantages. Figure 6 analyzes scaling with integration steps, plotting success rate versus step count across 4 tasks. Performance climbs sharply from 2 to 4 steps, and often peaks around 8, which suggests iterative compute adds useful capacity. The ant maze giant panel dips at higher steps, indicating diminishing or negative returns because excessive targets can overfit. Across all panels, floq remains above the dashed FQL baseline. Wrapping up, 2 takeaways stand out. Turning the Q function into a velocity field enables dense, stepwise supervision that lifts offline performance by about 1.8 times, and the integration depth becomes a practical compute knob for scaling capacity. The broader implication is simpler, more reliable critic scaling for difficult reinforcement learning. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.